good afternoon, everyone. My name is Brandon Rogers, and today I'm going to be speaking to you about the filter wash pump control system. First of all, today I'll be speaking to you a little bit about the background on the system, and then I'll tell you a little bit about how the input works and how you get an output. Then I'll describe the objectives of the system that we faced, and also describe the results that we came up with from the steady state operating curve along with the step response. Okay, basically the filter wash station is a mock-up system of the sewage treatment plant system locally here. Basically there's a pump system which pressurizes water to clean filter media, which filters out sewage, which is transported to the landfill. So in the system, you give a certain input as the controller, and you get an output. The input in this system is electrical power input from an electrical motor, which controls the pump, and the output is the water flow rate. The objectives of this experiment were to achieve a steady state operating curve in order to explain more about what output you can get from the input, and also in the transient flow, find out the system's dead time and how long it takes for it to respond when you do the step up with the inputs. In the steady state, I'll show you a brief example of what we came up with. For 68% input, we came up with an average of 23.8 pounds per minute as an output, and our uncertainty was about 1.6 pounds per minute. From the graph you can see, once you achieve an average, you can determine from what percentage input can give you a certain output. We also summarized all of our graphs into one graph in order to explain the system better and be able to apply a linear regression to the line. And as you can see down here, around 67%, we achieved a steady state, and all the way up to around 98%, which is around 23 pounds per minute and 38 pounds per minute. So basically you can apply an equation to this to where a certain amount of input will give you a certain amount of output on the system. Basically, the steady state region is found by identifying when the data within the graph reaches a constant range. So whenever you get little variation in the output, you can determine where your steady state region is. And in the transient flow, the initial output percentage, you can apply a dead time, also a gain, which is, I'll show you in the next page, and the steady state time. This is the graph which shows you all the parameters of the step response, and this is based on a 20% base with a 7% step at 10 seconds. And as you can see, delta M is the difference between the input and out between the step, and delta C is the difference between the step on the output, and T0 is the dead time, which is how long it takes for the system to respond to the step, which is actually supposed to be a little bit closer to this area over here, and that's about 0.9 seconds or so, which isn't too bad. And tau is the time constant, which determines when the system leaves the steady state region from step 1 and goes around 63.2% of the output step. This graph shows you what's the gain along with the response time and the dead time. And as you can see, it's pretty fairly constant all the way across. We didn't include the point on the steady state operation curve, which was not linear. So once you get all your data, you can pretty much refer each graph to the other. To conclude, the output range was 20 to 38 pounds per minute. The input range was 65 to 98% for the output range of 20 to 38 pounds per minute. Based on this data, there's little variation in the gain dead time response time for each experimental range, so it's very easy to compare one to the other and know how to relate to the system. And that's it.